In this module, we're going to learn how soaps and lotions work as well as what they're made out of. Um, when we start to thinking about soaps and lotions and we do just a general kind of Google search, right? You're going to find a wide variety of information. And so, just as I was setting this up, I did a quick Google search on different skin types. And so, we can see things like here with Youth to the People, should people with oily skin use an oil based cleanser, right? And so, we have these oil based cleansers. And some people have oily skin. And then we have people who have dry skin, right? And so, we have the different soaps that they use here. Other things that you can see on the market, particularly that have been a relative newcomer, have been kind of these charcoal soaps. And I spent tens of minutes kind of investigating, does the charcoal really work, and how is charcoal better than just a normal soap, right? And basically they talk about this activated charcoal, and I went to Google Scholar to look at peer-reviewed journals. And so you can see here's clinical dermatology. And basically, right, there's a lack of evidence to support its exfoliative or anti-aging abilities. And so one of the things that we have to be careful of when we start to look at soaps and different types of soaps and the best soaps for us, and some of the questions that we need to ask ourselves is someone trying to sell us stuff with some of these articles, right? And does that influence, of course, what we buy? But are we really buying the things that are the best for who we are? And that's something that you can look into for your final project if you're interested in, and we can talk about that more later. But so I've digressed a little bit, but let's start to talk about oil and water and just some information that we know, right? And so when we think about oil, right, versus some more water-based soaps, what do we know? Well, one of the big things we know is that oil and water do not mix, okay? And so when we talk about this, maybe the burning question in your heart is why? Well, oil is non-polar, right? While water is polar. And I have an image there of oil being added to water. And this is something we're really familiar with. We know that the most dangerous time to drive is right when it first starts raining, because all the oils that are on the road float to the surface and it becomes really slick because the oil and water don't mix. Well, I want us to give some definitions to a polar molecule and a non-polar molecule. A polar molecule is just a molecule where one end or area of the molecule is more negatively charged than the rest of the molecule. Okay. So basically, with a polar molecule, we have an area that has some sort of charge and that's more negatively charged, and an area that's more positively charged, right? And just kind of like if you think about a battery or a magnet having poles, it's that same kind of principle there. Now, on the other hand, we can also have non-polar molecules, and these have an even distribution of electrons over the entire molecule. Okay, so oils are going to have this even distribution of electrons over the entire molecule, whereas water will have one end that is more positive than the other end, or one negative than the other end. So what determines, right, what's more positive and what's more negative? Well, it turns out when we look at this, right, and we're trying to figure out if things are polar or non-polar, in general, Small nonpolar molecules fall into three categories. And we're going to list them here, but then we're going to look at these three categories, two of the categories in this screencast and one in the following screencast, right? So small nonpolar molecules are molecules that just contain the same atom, okay? This would be something like hydrogen, H2, chlorine, sulfur, these types of molecules, right? So it's the same atom, okay? The other thing that we see, small nonpolar molecules, if a molecule just contains carbon and hydrogen, it's nonpolar, right? So this would look like something like this: CH3, CH2, CH3, or it could be something like this: C5H6. Those are nonpolar molecules, okay? And then the third kind of category that we have is symmetry. And we are going to talk about symmetry in our next screencast. In this screencast, we're going to focus on why are molecules that have the same atom nonpolar, why carbon and hydrogen, why are those nonpolar when other things are considered polar? Well, let's start with number one here. If you've got bonds between the same atom, why are those nonpolar? Well, they have the same electronegativity. And so maybe you're like, "Ooh, that's great, Dr. Pierce, the same electronegativity." Well, what is electronegativity? Electronegativity right, is just the ability of an atom to attract the bonding electrons. So when I say bonding electrons, these are the electrons that make up a single, double, or triple bond. Of a covalent bond to itself, okay? So this atom, if it's super electronegative, will kind of like suck all the electron density through the bonds from all the other atoms, right? That's it. And we can use the periodic table to help us predict which atom is more electronegative than the other. So the atom that's the most electronegative, so I want to say it this way, the most electronegative atom is fluorine. So fluorine is 100% the most electronegative atom. And as a matter of fact, electronegativity increases as you move closer to fluorine. And we can use the periodic table to help us look at this trend. So when we talk about like there being a trend and we're looking at the periodic table, there's a few things I want you to notice. The first thing I want you to notice is when we're talking about electronegativity, we ignore the noble gases. They're very unreactive. So we're just going to ignore them. Fluorine here is our bright shining star. We could even say she is a diva, right? And she wants all the attention from the electrons, so she's going to attract all the electrons to herself. And what we see is that electronegativity increases as we go up a group, right? And across a period to where fluorine is the most electronegative. Atoms that are elements that are here, kind of in this lower left-hand corner of the periodic table, are the least electronegative. So this helps us determine if things are covalent, if things are polar or nonpolar. I want to point out when we talk about things being polar and nonpolar, we're really only talking about those covalent molecules that we talked about in Module 2, okay? Ionic, we'll talk a little bit about ionic compounds coming up, but when we're talking about polar or nonpolar, these are covalent bonds that we're talking about. So when we talk about a polar covalent bond, right, It's just a covalent bond where the electrons are not shared equally. Okay. And then in a nonpolar covalent bond, the electrons are shared equally. And the numbers here that are associated with the electronegativity values help us understand if things are being shared equally or unequally. Okay, and so you do not have to memorize these numbers, right? If we use them in class or they're given, they'll be given to you. Okay, but let's talk about how we do use these numbers to figure out if things are being shared equally or unequally. Okay, so I want us to visualize this just a little bit. So what you see here are two molecules. We have H2, right? It's two of the same element or same atom type. It's a nonpolar covalent bond. These are going to share these two electrons that make up this bond equally. Now, look at chlorine. When we look at chlorine here compared to hydrogen, and we look at the values of chlorine and hydrogen. So we go back and look at chlorine's electronegativity value. That's a 3.0. And then we look at hydrogen's. It's a 2.1. And we take and we look at the difference between these two. We just subtract. That's 0.9. And that number is going to mean something in the next slide. But that difference there tells us that this is a polar bond. Okay, so the difference between the fact that these numbers are greater than 0.4, that to us means it is a polar bond. So what does that mean? Do you see how these two electrons are here right in the center between the hydrogens? Here, these electrons that make up the bond between the hydrogen and the chlorine are closer to chlorine, right? And so chlorine holds on to that electron from hydrogen a little bit more tightly. So some ways that we represent this are with these delta values. So the deltas themselves these are lowercase deltas. They kind of look like a squiggly S. And the one that has the greater number, the electronegativity number, gets that delta negative. A lot of times we will call this, right, more electronegative. Right, or the more electronegative side of the atom. And then we'll call this side electropositive a lot of times. Okay, and that has that delta positive that's shown right here. Another way we can show this is by putting a little positive here where we have the electropositive atom and drawing an arrow to the more electronegative. This is referred to as a dipole, right? Moment arrow. So let's look at why molecules that are just made of carbon and hydrogen are nonpolar. So when we look at the different bond types here, we've learned from their previous chapter, we have covalent molecules and ionic molecules. And covalent molecules have two different types. You can have nonpolar and you can have polar. In ionic molecules, there aren't two different types. Basically, what happens is if you have an electronegativity difference over 1.8, the electrons just transfer, right? The atoms themselves are no longer sharing the electrons. They're just going to transfer them. When you go back and look at the electronegativity values, you'll notice your metals have very low electronegativity values. And so that's one of the reasons why we can make a generalization that if you have a metal and a non-metal, they will form an ionic bond, is because this difference will be over 1.8. So they will form this ionic bond with just electrons that transfer. Here, really the dividing line between something that is nonpolar or polar is it's going to be polar if it's above zero point 0.4. So the difference between those atoms is above 0.4, it will be polar. So if the difference between the electronegativities are above 0.4, then the bond is polar. Okay, now it needs to be above 0.4. If we look at carbon and hydrogen, like a carbon and hydrogen bond here, carbon's value of electronegativity is 2.5, hydrogen's is 2.1. When we subtract these, we get 0.4, right? So that is considered a nonpolar bond. Let's compare that to like carbon and fluorine, right? So fluorine here is 4, carbon is 2.5. When we go through and subtract these, 4 minus 2.5, we get 1.5, right? And that is over here in this polar area. So electronegativity can help us figure out if bonds are polar or nonpolar. Some common questions I get: hey, Dr. Pierce, how do you know which of these two numbers goes first? You're just going to arrange it so that whatever you get is positive here, right? That's how we're going to deal with that. The other question I get is, hey, Dr. Pierce, we've been talking about bonds. How does this apply to molecules, right? Because molecules can be made up of lots of different bonds. Well, not to leave you on a cliffhanger, but to leave you on a cliffhanger, that's where symmetry comes in. And we're going to talk about symmetry in our next screencast.